Good morning. Hi, good morning. In today's lecture, we will illustrate yet another application of integration. We will derive a formula for arc length. Let me set up our problem. So let's say that we have a graph of some function f between a and b. And we're interested in the length of the graph of f on AB. Let's assume that f is smooth. That is, let us assume that f prime be continuous on AB. Then the graph or the curve y is equal to f of t on AB is given by the following formula. The integral from a to b of the square root of 1 plus the derivative of the function squared dt. So this is the main formula in today's lecture that we will use to find lengths of various curves. Let me start with a very basic example, and then I will define formally the arc length, and I will derive this formula. In our first example, let's calculate the length of this curve, 2/3 t to the power 3/2 between t is equal to 3 and t is equal to 8. I'd like to give you a second to try to apply our arc length formula. And if you are interacting with us online, it's a good time to pause this mini lecture. Okay, let's do it together. So we get the integral from 3 to 8 of the square root of 1 plus the derivative squared dt. So I need to calculate the derivative of this function. So we got 2/3 times t to the power 3/2, and then we need to take the derivative of this expression. 2/3 is a constant, so I can take it outside. And the derivative of t to the power 3/2 is, what is it? If it was t to the n, is n times t to the n minus 1. So in this case, we got 3/2 times t to the power 1/2, which is t to the power 1/2. So then we get the integral from 3 to 8 of the square root of 1 plus t dt. So now we need to guess the antiderivative of this integrand. Those of you who already know integration by substitution, you could use the u substitution here. You could let u to be equal to 1 plus t. But we have not covered integration by substitution yet, so we could guess an antiderivative and then see if our guess is correct by differentiating. And if our guesses will not be correct, we can resort to Wolfram alpha, in any case in today's lecture. So if I had a square root of t then you know that the integral of the square root of t dt is equal to t to the power 3/2, 2/3 of that, right? So what would be an educated guess for the antiderivative of the square root of 1 plus t? Yes? 2/3 t plus 1 to the 3/2. So let's check if that's the case. So to check if our guess is correct, we need to differentiate the right-hand side. C is a constant, so of course the derivative of this part will be 0. I can factor then the constant 2/3, the derivative of this function. How do you differentiate such a function? The chain rule. Why the chain rule? Because 1 plus t to the power 3/2 is the composition of two functions, the inner one of which is just a linear function, just add 1, and the outer one is raising the argument to the power 3/2. So first the derivative of the outer function times the derivative of the inner function. The derivative of 1 plus t is 1, right, with respect to t. So in fact we get 1 plus t to the power 1/2, which is exactly this. So yes, our guess is correct. In other examples where guessing will not be as easy as this one, please use Wolfram alpha to get the antiderivative. However, I would like you to show the rest of the calculation. Okay, so here now we get 2/3 1 plus t to the power 3/2, and this needs to be evaluated at 3, at 8, and you take the difference. So we got 2/3 1 plus 8 to the power 3/2 minus 2/3 1 plus 3 to the power 3/2. Okay? So 1 plus 8 is 9. 9 to the power 3/2. How do you calculate that? I can take 9 to the power 1/2 and then raise that to the third power, right? So what is it? 9 to the power 1/2 is 3. 3 to the third, 27. So I have 2/3 times 27 minus 2/3 times 4 to the power 3/2. It's 8. Okay, so we get, what do we get? 2/3 times 27 minus 8, that's times 19. So that's 38/3, or 36 divided by 3 is 12 and 2/3. So that's the answer. What I find amazing about this example is that even though you actually have a curve, the final answer for the arc length is just a nice rational number. Why do I find it amazing? Well, you know, the first curve that I've ever whose length I ever knew was obviously a circle. And the arc length of the semicircle of radius 1 is just pi, and pi is an irrational number. That is a number that cannot be expressed as a fraction of two whole numbers. Let's now define arc length and try to derive the main formula in today's lecture. We are now going to define the notion of length, and we will derive this key formula in today's lecture. So I sketched some curve y is equal to f of t, defined between a and b. And let's ask ourselves how we intuitively would calculate the length, or measure the length of this curve. One approach, perhaps, would be to try to straighten it out. And then measure the length of this rectified curve. So I get 25.5 inches. And that's it, right? Well, you could probably convince someone that this is a good approach, but not me. Because what we just did here, in order to describe it precisely in the language of mathematics, would require calculus. Anytime you deal with curves such that no matter how much you are going to zoom, you will never see a piece of a line segment, then you have to use a limiting process, a process of approximation. So another approach is this. We will come up with the sequence of numbers, numbers that will have a pattern, numbers that will have a limit. And that limit will be the length of the curve. So how will I come up with these numbers? Well, the first approximation could be just measuring the distance between the endpoints of the curve. So we write down this number. But then we could do better. We could subdivide our interval AB into, say, n pieces, and each piece will have length delta t. And then we mark on the curve points corresponding to our subdivision. So say this would be point P1. Maybe that could be point PI, and this one PI plus 1, etc. So then our approximation would be the summation of the distances between the consecutive points on the curve, these points pi. So that could be our approximation, right? And now if I let delta t go to 0, all these subintervals have the same length, then n goes to infinity, I will get many more points on the curve. And then these segments will better and better approximate those portions of a curve. For example, if I were to zoom a small fragment of this curve, then the line segment joining two points that are pretty close, the length of it would be probably not much less than the length of the union of smaller segments. In other words, what we're looking for is we're looking for the limit as n goes to infinity of the summation when I varies from 1 to n of the distance between points pi and pi plus 1. And that limit, if it exists, will be the definition of the length of the curve y is equal to f of t. Well, this limit, even though we state it precisely, we state even though this quantity makes sense in calculus, it's kind of hard to use it for practical purposes. So what we should do now is to try to use some properties of our function f in order to make that calculation easier. Well, let's see if we can rewrite the length pi plus 1. So I'm talking about this length here. I know that if I project that segment onto horizontal direction, then its horizontal projection will have length delta t. But what about its vertical projection? What is this length? Why am I doing this? Well, why am I doing this? Because then I can use the distance formula, or a Pythagorean theorem, if you will. Once I have the base and the height, I can get the length of pi plus 1. So if I knew the slope of the line joining pi and pi plus 1, then I know the height, right? The height will be just that slope times delta t. So how do we get the slope? And here is where some theorems from Calculus 1 are quite useful. Well, we'll use the mean value theorem in order to get that slope. Does anybody remember the mean value theorem? Let me remind you what the mean value theorem states. So if we take 2 points on a graph of f of t, say pi and pi plus 1, then we look at the line joining these 2 points, and we translate it in a parallel fashion until its translate becomes a tangent to the graph of f. And the mean value theorem states that you can find that point between these 2 points, pi and pi plus 1. So, in other words, there is some number ti star such that the derivative f prime of ti star is the slope of the segment pi plus 1. So now let me go back to my question here. What is the height of this triangle? It's the slope times delta t, right? So that would be f prime of some number ti star times delta t. Okay, so now we can continue discussing our summation. So instead of the length pi plus 1, I will use the distance formula, or Pythagorean theorem, if you will. So how does it go? It's the square root of delta t squared plus the height squared, right? So f prime of t I star delta t, all of it, squared. What do I do next? I can factor that delta t squared, right? So I get the limit as n goes to infinity of the summation as I varies from 1 to n of the square root of delta t squared times 1 plus f prime of ti star squared. Now I can factor the delta t squared outside of the square root. And then I get the limit as n goes to infinity of the summation I goes from 1 to n of the square root of 1 plus f prime of t I star squared. Oh, delta x, of course. Delta t. So notice that this is reminiscent of something we've seen before many times in Calculus 1. This is actually the limit of a Riemann sum. The Riemann sum of the function, which is the square root of 1 plus f of t. So that's a new function. You can call the function g, which is the square root of 1 plus f of t squared, f prime of t squared. And then you have the limit of the Riemann sum of g. In other words, this is the integral from a to b of the square root of 1 plus f prime of t squared dt. But that's exactly the formula that I introduced in the beginning of the lecture. In Leibniz notation, the arc length formula becomes the integral from a to b of the square root of 1 plus dy by dx squared dx. I have to give you a fair warning that, so who set up the integral? Okay, let's do it together. So the length of the upper semicircle will be the integral from -1 to 1 of the square root of 1 plus the derivative of the function, the square root of 1 minus x squared, right? So let me calculate this derivative. How do we get the derivative of the square root of 1 minus x squared? We apply the chain rule. So here we have a composition. We have the composition of x goes to 1 minus x squared, and then we take the square root of that. So the outer function is the square root function. So what's the derivative of the square root function? It's 1/2 the argument to the power negative half. But that's not it, right? We need to multiply this result by the derivative of the inner function, the derivative of 1 minus x squared. 1 is a constant, so just differentiate negative x squared, and then what do we get? Negative 2x. So 1/2 and negative 2 gives me a negative sign. So I get x divided by 1 minus x squared to the power 1/2. Okay. So I can write down this derivative in our formula. And now let's try to simplify the integrand. What do we get here? We square the numerator, and if I square the denominator, what do I get? 1 minus x squared to 2 plus 1/2? No, 2 minus 1/2. Okay, can somebody explain why this is wrong? You're not adding or subtracting exponents here. You're actually multiplying them. So you get 1 minus x squared dx. Okay, now what do we do with this? Common denominator. What's the common denominator? 1 minus x squared, right? So I get 1 minus x squared divided by 1 minus x squared plus x squared over 1 minus x squared dx. So I get the integral from negative 1 to 1 of the square root of, if I have a common denominator here, 1 minus x squared, what do I get in the numerator? 1 minus x squared plus x squared, so just 1. Okay, so we got that integral, the integral from minus 1 to 1 of the square root of 1 minus over 1, the square root of 1 over 1 minus x squared dx. Do you guys remember where this expression appeared in Calculus 1? It appeared when we talked about inverse trigonometric functions. Remember that the derivative of inverse sine is precisely the square root of 1 over 1 minus x squared. So how do we complete this problem? Well, we need to evaluate inverse sine at 1 and at negative 1. So we get sine inverse sine of x, evaluate it when x is equal to negative 1, then evaluate it when x is equal to 1, and then we take the difference. So we have inverse sine of 1 minus inverse sine of negative 1. What's inverse sine of 1? So in other words, what is the angle between negative pi divided by 2 and pi divided by 2 such that sine of that angle is 1. It's pi divided by 2, yes. So we get pi divided by 2 minus, and what's inverse sine of negative 1? Negative pi divided by 2. Okay, so we got pi. Well, I'm so happy. Didn't make a mistake here. There are several homework problems. And again, as I mentioned before, if you get stuck with trying to get the integral, use Wolfram alpha to get the antiderivative. But I'd like you to show me the work leading to the integral. So I'd like to see how you set up the integral, how you calculate the derivative, and so forth.